Right. Hello, everyone. Welcome to the next installment of our geometric PDE seminar, continuing on with sort of mean curvature flow with surgery. Today, James Stanfield is going to tell us about necks, which are very important to understand to get an idea of singularity. So over to you, James.
Thanks, Paul. I must admit, I've been banging my head against this Priskin Sinistrari paper for a few days now, and I'm still not sure of all of the details. So if anyone has anything that they want to pitch in throughout or enlighten me and everyone else on, I would appreciate it. But yeah, so let me outline what we're going to do today, and I'll start with what we've done so far. So let's take some mean curvature flow. Okay, let's make it 2 convex. Okay, we're sticking to n larger than or equal to 3 for the moment. And let's consider the eigenvalues of the second fundamental form. So what have we done so far? So there's a few beautiful estimates we've shown that are going to be crucial for us. So they take the form of, so you have some delta greater than 0, then there is some constant depending on delta and the initial hypersurface, such that the following holds. So first of all, we get kind of a convexity when we blow up at a point, when the curvature goes large, right? So we get this nice convexity estimate. So if we rescale around a region of high curvature, we're going to yield a surface which is convex. That's what that means. And then the other estimate is that we get some cylindrical properties showing up. So we're always going to have lambda1 positive when we go to the rescale limit. But suppose that lambda is not too large, right? I.e. it goes to 0 in the limit, so to speak. Well, then our other eigenvalues are going to be close to each other. This is something we've proven in the last few sessions. Okay, so this is a all right, good. This is a cylindrical estimate. Okay, and so the idea is when the curvature gets very big, the eigenvalues, this would be ij larger than or equal to 2, the eigenvalues in the directions where, or in the other directions are going to become very close, okay? And so intuitively, we're going to expect a cylinder forming here, okay? There's kind of a bad situation that can occur, and that's where the next estimate comes in, our gradient estimate. So this is what we did last time. So there's a constant, like a small c and a big C, such that we can bound the gradient of our fundamental. And the way this is going to help us is in this bad situation where we have kind of this this spherical cap forming. So suppose we pinch like this sort of degenerate neck pinch coming in like this. So you can imagine at this point, H is large, but lambda1 is still large, right? So here we wanted lambda1 small, but lambda1 in this situation is still going to be large or not small. And the idea is we're going to use this gradient estimate to show that in some controlled region, some controlled distance from this point, there is going to actually be a cylindrical part. So within some controlled distance, we will actually be able to find a little cylinder. Okay. So we're expecting these estimates to really help us out here in the long run, but what we need to do is make precise how we go from these estimates on curvature to actually constructing, say, a cylindrical parameterization in part of the manifold. So that's what we're going to be doing today and probably next time as well. Okay, so today, we're going to look at two kinds of necks in detail. So the first one is the so-called curvature neck, which is what we're kind of seeing already when we look at our two-convex mean curvature flow, right? So that means, roughly speaking, that our second fundamental form is like that of a cylinder. Okay, so there's one small eigenvalue and the others are very close to each other, maybe in some ball. And we also know that it's approximately parallel, right? Which what we'd expect because that's what holds for the cylinder, right? Maybe to be precise, we want all the derivatives to be close to zero. Okay, so that's kind of like the idea of a curvature neck, some region where the curvature looks like that of a cylinder. And then we've also got topological necks. Okay, so that's like a local diffeomorphism from the cylinder into our hypersurface, right? With some control on the CK norm, say, or CK. Yeah, with some control on that.
Cross
okay,
R,
so
right?
Yes, sorry. Cross some interval I. Yeah. So yeah, we want to go from a region where the curvature looks like that of a cylinder, and then we want to construct an actual embedding, right? So that's our goal today. Right, so if you have a large enough curvature neck, then we want to construct a topological neck. Okay, so the proofs get kind of technical, but this is the big picture. So are there any questions on the big picture? Cool. So we'll jump in.
So
and we'll
James,
define
quick question. Sorry.
Yeah, you're right.
Do you want the boundary? I mean, just want this diffeomorphism, nothing else, right? You don't want this the boundary to be incompressible. I mean, it's just a diffeomorphism, just coordinates in the cylinder somehow.
Yeah, I mean, I'm being
Okay.
very vague here, right? But there is going to be probably next time there's this kind of like canonical parameterization you can do around these things, and you get all these conditions on like the spheres in the pullback metric have to be harmonic, etc. Like you get all these
Yeah, of
extra
course.
things. Yeah.
But nothing more topologically speaking, nothing else. Okay.
No, I don't think so.
Yeah. In fact, you expect to be doing surgeries which are not topologically needed, right? So you can have, you could start with a sphere with a bump in it and you'd still get a neck forming, certainly not incompressible or anything like that, but you still have to do the surgery to continue.
Right. No, of course, yeah. But sometimes, but this is probably more relevant in the collapsed picture when they look at the locally incompressible stuff.
Yeah, that's right. Yeah.
But not relevant, I guess, for this non-collapsed situation.
That's right. Yeah.
Okay, cool. So yeah, I've got about 10 different definitions for everyone to keep up with. So let's just consider some hypersurface, let's say immersed. And I'm going to call W the Weingarten map. Okay, so remember that's just defined like this. Okay, maybe technically speaking, you want to do that up to some sign. I think that's the right sign. Yeah. So definition. And this is just making precise what I've been talking about already. So the extrinsic curvature is, so first of all, we'll call it epsilon spherical at P if, well, if what you expect happens, right? If the Weingarten map looks close to the identity. Okay, so that will be important. Epsilon cylindrical if, well, the Weingarten map looks like that of the cylinder, right? So let's do blue maybe. So WP minus, say, W bar is less than epsilon, where this is just the Weingarten map for the cylinder, right? So in some standard frame. So let me just remark, I want the cylinder of radius 1, so I'm not worrying about scaling yet. I just want to ask if it's close to a cylinder of radius 1. Okay, and so you have to obviously line the cylinder up properly so that these match up, and then if you can do that, we call it epsilon cylindrical. So now we want some higher order conditions as well. So we say it's epsilon k parallel if it's nearly parallel everywhere, right? So WL, sorry, not WL, tablet L. Okay, so makes sense. And then we want epsilon k spherical on M if, well, the obvious happens if it is epsilon spherical and epsilon k parallel everywhere. Okay, so you want it to be very close in the CK norm to the Weingarten map of the sphere. And last thing, and this is kind of the most important one, we say epsilon KL, so 3 parameters, epsilon KL cylindrical around P in M if it is epsilon cylindrical and epsilon K parallel on the intrinsic ball of radius L around P. Okay, and then we'd say here that P is the center of an epsilon K L cylindrical, or say epsilon K L curvature. Okay, so this is what I mean by curvature neck when I said it before. I mean that it's everywhere the Weingarten map's epsilon close to that of the sphere, and the curvature, the kth, so well, all the derivatives up to the kth derivative of the Weingarten map is bounded by epsilon. Okay, so hopefully these are fairly intuitive. We're just saying that, yeah, the curvature is close to that of a cylinder. Cool. Any questions regarding those definitions? Okay, so today, basically we have two propositions regarding these, both of which I don't fully understand. And we're going to, first of all, characterize what happens when a manifold is epsilon k spherical. And basically the obvious thing is going to happen. It's going to be parameterized by a sphere. So you're going to have it written as a graph over the sphere, and the function that you write it as a graph of is going to be very small in the ck norm, right? So let's just write that out properly. So this is proposition 3.4 in the paper. So for k greater than or equal to 1 and some small enough epsilon, if some hypersurface is epsilon k spherical, so I'll write here epsilon k spherical on some ball of diameter greater than 4, or of radius bigger than 4. So we only want it to be epsilon k spherical in some big enough region, then M is closed, uniformly convex, and given by the graph of a function over the sphere, right? So of U over the sphere Sn with a controlled ck norm, or ck plus 2. Okay, so the interesting thing to me is that you only ask this to be true on a ball of radius d bigger than 4. And that turns out to be crucial. I think you do need completeness, but it doesn't seem to be used on a complete surface later on. So maybe, or on an a priori complete
the
thing.
4 is
Yeah,
related to the fact that the diameter of the unit sphere is clearly bounded by.
Yeah, no, that's definitely what it is. Anything bigger than pi would work here. We'll see in the proof. You use Meyer's theorem, but the issue I have is that one, I don't know of any version of Meyer's theorem that only asks for a curvature bound in some region. And two, I'm pretty sure completeness is quite essential. So I don't know. To me, like, completeness is essential because you could just look at a sphere and take a point out and it would satisfy the assumptions of this, but it's clearly not spherical, right? So I don't know.
The assumption is probably that geodesics can be continued for a length at least 4, right?
Right, okay.
From P. Yeah.
But does this punctured sphere still break that, or?
Yeah.
Sure.
Yeah.
Yeah. Anyway.
But I assume M is complete here, right? So.
Well, that's the thing.
For the proof you can, but later on they might need it not to be. I think that's all.
That's the issue for me.
Yeah, I think for the proof it should be enough to assume that you have a manifold where the exponential map is defined on a ball of radius 4.
Okay.
About some point.
Yeah. Let's do the proof and see.
Let's try it. Yeah.
Yeah. So let's just choose epsilon of n small enough. Okay, so we want to choose it small enough so that W is really close to the identity to give us uniform convexity, right? So that say all of our eigenvalues are between these two numbers. Okay, so this is just coming from and strictly speaking, this is true in the ball where this is happening on. So clearly this implies uniform convexity. Okay, and you argue from there that you have a positive lower Ricci bound. Again, in fact, because of these, you can work out precisely what that lower bound is. So that implies by Meyer's theorem. So here, I feel like you need some more general version of Meyer's theorem than the common one. That M is already diffeomorphic to Sn, and the diameter is bounded by 4. And the diameter being bounded by 4 is coming from the precise constant you work out from there. Okay, so just a reminder, Meyer's theorem is that if you have this, then the diameter has a bound.
I think
strictly
in the proof of Meyer's theorem, you grab any minimizing geodesic, right? And then you apply the second variation and then there's curvature appearing, and that's precisely the assumption. So that with that you estimate. So it doesn't seem to need completeness. Right? It does tell you something about the length of any minimizing geodesic under these curvature assumptions.
Yeah, I mean, it's saying that there has to be conjugate points inside this ball. But I don't know how you argue from there that it's diffeomorphic to Sn, but maybe, I mean, intuitively, I guess it makes sense, but yeah, I'm not sure.
Ben, you are muted.
Sorry, yeah, I think you're right, James, that you probably can't just apply, if you're not assuming completeness, you probably can't apply the usual form of Meyer's. But here you have a lot more control using this approximate center that I guess you're about to talk about. And I think you can rescue things with that.
Right, yeah, sure. Okay, well, I'm just not sure of the details. Yeah, I'm convinced that it's probably true. I just don't know the details of doing it properly. But hopefully this gives the right intuition anyway. So from here, we kind of, as Ben said, we're defining a kind of approximate center function. So this Z, which goes from M to Rn plus 1, we're going to take a point P, and we're going to do P minus N over H of P. This is well defined because we're uniformly convex, times the normal at that point. Okay, so you can imagine we kind of look like this. And this is going to map out like a little, the image of Z is going to kind of look like this, right? So approximately, we're going to be at the center of some sphere. That's why I call it an approximate center. Okay, and so if we can show that this approximate center doesn't oscillate too much, then it makes sense that we're going to be able to just pick some point on here and then just write the graph over the sphere. And because this point is within a controlled distance of the rest of the points on the center, this U that will define our graph is going to not move too much, which is what we want. So how do we do that? Well, if we look at the derivative, so this is kind of like doing this derivative. Well, it is exactly this derivative. So we're trying to show a derivative bound to make sure we get a C0 bound. So if I differentiate this, I get the vector EI minus, okay, so I want to differentiate the normal in the direction I, and that's just going to give me, by definition, the Weingarten map acting on EI. And then I have to differentiate this part, so I get N on H squared, nabla I H nu. Maybe you need a plus there. Okay. And then, well, we split this up, right? So, I mean, I do the usual epsilon 3 type argument. I get the following. Yep. And then okay. So maybe just doing one more line, I get 1 on h minus n plus n on h. Just to make this crystal clear. Okay, so this I can make small because all my eigenvalues are close to 1, so their sum will be close to n. So this is small. Obviously, this is small by assumption. W is very close to the identity. And finally, this is very small because I'm assuming that I've got a CK bound on W, right? So this is all less than or equal to some constant depending on n times epsilon. Okay. So in particular, the oscillation of Z is clearly bounded by some constant times epsilon. This is why we wanted our diameter bound, right? So we get that Z doesn't move around too much, so we can just fix some P naught in N and define U, which is going to be our graph. It's just the sphere of radius 1 around this center, which we'll fix, and this is going into R. So as I said, we fix, maybe I'll copy this down here. So we fix a P naught, and this is Z of P naught. And then we have the sphere around it. And then because Z doesn't move too much, we see that U, which is going to be kind of representing this little bit in here, U is going to be very nice and controlled. Okay, so we just do this appropriately. Then U has a C0 bound. And then the other derivatives, well, this is going to come from our bounds on W. So we have a CK bound on W. Okay. And then W is like second derivatives of U, so to speak. And so this is going to quickly give you CK plus 2 control of U as we wanted. So from there, the proof's not too hard, right? We're just using all the properties of our curvature to show that this approximate center doesn't move too much. And then you can write, you can put the sphere around that, and you can show your graphical representation doesn't move too much either. Any questions on that theorem or the proof? So this is where it's, we're going to use it to prove the next theorem, which I think is kind of the crux for doing surgery in a way. This is where we're going to identify a topological neck from a curvature neck. So this is 3.5 in the paper. So let's just take K bigger than or equal to 1 again. So let's take L bigger than 10. And then there exists some epsilon depending on L and some constant. Such that the following holds: if P is the center of, and then we want an epsilon k L curvature neck. So remember, that means that everywhere the Weingarten map looks like that of the cylinder, the kth derivatives of W are bounded by epsilon, and that happens everywhere in a ball of radius L around P. So we're basically in the situation we expect to find when doing the mean curvature flow. So where epsilon is between 0 and this other predefined one, then what holds? Then P has a neighborhood given by the graph. So like before, so we wrote a graph over a sphere, and then what we expect here is a graph over a cylinder. So we get U, which maps from the cylinder, and we come away from the ends of the ball a little bit. And then again, this also has C k plus 2 control. And that's where our C comes from. Okay, so as I said at the start, we wanted to go from curvature necks to topological necks, and this is exactly the statement that does that for us. Okay, so any questions on the statement? The proof will take us to the end of the talk, so we can get started on that. So similar idea to before. Basically, what we're going to do is prove that there are two parameterizations, one for a cylinder and one for the neck, and one for the manifold locally. We're going to show that in the CK norm or CK plus 2 norm, those parameterizations are very close to one another. And then what you can do is go along the parameterizations. You know they're very close. You can look at cross sections of the manifold's parameterization. And then you know that they approximately look like spheres, right? Because everything's very close. So they look like spheres. You apply the previous proposition to get that you get a spherical parameterization there. And then because our assumptions on W are so good, we basically can glue these parameterizations together and we get a full thing for the cylinder. So that's the heuristic, and then the details get hairy. So again, we make our epsilon of n small such that, well now, so we're asking that the Weingarten map is close to that of a cylinder, right? So we can make lambda 1 very small and the others very close to 1. Okay, so that's what we can do there. And we want that everywhere in the ball of radius L. Okay, but what this gives in particular is that lambda 1 is certainly not equal to lambda 2, right? So that means there's a well-defined eigenvector. Okay, and so now we want to consider the cylinder that lines up with this eigenvector for lambda 1, right? So F bar.
So when you say well-defined, you mean it depends mostly on P? Or?
No, I just mean there is a unique eigenvector for lambda 1, I guess.
Okay.
So maybe I'll just say is the. But yes, I think you're right. You'd get some sort of nice distribution going on, right?
Yeah, because there's no crossing of eigenvalues, right? So then the eigenvector will depend more.
Yeah. So I guess you get even more, but I don't think you need it. But we'll see. So they remark in the paper that the proof in the hypersurface case is a little bit easier than Hamilton's proof in the intrinsic case, right? So it looks a little bit different, I think. So we consider this cylinder. We want to touch M at P, and we want it parallel to, say, E1 of P, and matching orientation, right? So the picture looks like this. This is our E1, and then we have some cylinder touching. And we want to show that, you know, basically the white and the green are quite close. Okay, and that should be enough. Cool. So let's also just label the normal here. Okay, and then we want to choose, say, an orthonormal basis, E1 of P, which I already defined, up to En of P, along with our normal, and we want that agreeing with the standard frame for the cylinder. Okay, so I choose basically a frame for both manifolds at that point. And then the idea is we want to parameterize both of these hypersurfaces on the same domain, so to speak. So we choose normal coordinates for both of them. And because I've got the same orthonormal frame for both of them at this point, it's a natural thing to do. So we choose normal coordinates. So we have G. So I'll just do it for our hypersurface. Okay, so remember this map takes X and we get the exponential. Along X, maybe I'll use B. Okay, so we choose normal coordinates, and then we want to take this frame that we have at this point, and we want to parallel transport it radially on both the sphere and on both M and the cylinder, right? So we go radial parallel transport along some geodesic. So I'll write X, P, R, C. And this gives us an adapted frame. So I'll call it EI of arc C, nu of arc C, which is just the normal at that point, right? So this would be F after G. So should say I want to take C with norm 1, and R is possible. Okay, so I'm choosing, so they have a shared tangent space here. And I'm choosing a C here, norm 1, and then I'm following this, say, along the white, and then also along the green. Okay, and we're going to show that these two parameterizations are approximately equal. So I'm going to abuse notation quite a bit, so I might refer to a vector in the tangent space when I really mean its parallel transport along a geodesic. So if you're confused, interrupt me, but it should be hopefully understandable from context. So because these are parallel along these geodesics, this leads to an ODE system. Okay, so this leads to an ODE system for the EIs. So what is this? So you use the fact that these are parallel. Okay, so again, I'm using C to denote the direction of the geodesic. So you know they're parallel, but of course the covariant derivative splits up as the covariant derivative in R. You subtract off the second fundamental form, right, which is precisely, what do we get? Minus, okay, and then we have our Weingarten map showing up again, by definition of the second fundamental form. Okay, so we get the following. So along the curves, we get this. And then you can use the relation that EI nu equals 0, differentiate this with respect to R, and you get a similar equation for nu. Okay, but then you can play the exact same game for the cylinder, right? So similarly, you have normal coordinates G bar mapping from Rn into the cylinder. Which gets mapped into Rn plus 1 by n. And then again, you extend the frame to say EI bar with and nu bar by parallel transport, etc. And this gives you another system of equations for this other frame, right? So I've got two frames. I probably should have drawn this in the same color. So I've got one frame being extended along here, and another frame coming down here. Okay, and they both satisfy very similar ODEs. So do it in green, because my cylinder's green. When I write bar, I mean, well, obviously I'm referring to the frame on the cylinder, and then here I mean the parallel transport of C along the cylinder, right? Nu bar. And you get a similar thing here. So you get W bar, C, EI bar. Okay. So now what happens? Well, because my gradient of my Weingarten map is so small, then I can integrate this, and I get that if I just look at P and then I subtract off the same thing after moving along, this is less than epsilon r. Now, strictly speaking, I'm comparing these at two different tangent spaces. So what I really mean here is that I'm parallel transporting back and then comparing, okay? So this covariant derivative bound gives you this bound here. Moreover, this is going to imply that I get a similar bound. So because well, okay, since if I evaluate at P, this is also less than epsilon, right? By assumption, I'm saying that the frame is less than epsilon when compared to P. This is going to give you like an estimate between the two Weingarten maps at different points on in the parameterization, right? So you get W arc C minus W bar arc C. You're going to get something like C of n epsilon r plus 1. So the reason we go to all this trouble is because these two ODEs really only differ in the W's here, right? Otherwise, they have the same form. I know there's different C bars and stuff, but because that's parallel transported from the same C on both things, that doesn't matter. So the point is that the data doesn't differ too much, and also the frames agree at the point. So what you get is a bound for the derivative. For this derivative, this is less than some constant. Okay, and that's just from computing with these ODEs, okay, and using this. Okay, and then because they agree at the point, we use ODE comparison. To get a bound on the difference between our frames. Okay, so this is less than a constant, depending on n and l times epsilon for that star. Okay, so that's a little bit of work, but turns out if we choose this normal parameterization for both of them, the frames don't differ too much, which makes sense. This is where things start to get a little bit more hairy. Well, not hairy, just a little bit more hand waving. So if we integrate the frame, so this bound in the frame will lead to a bound in the actual parameterization. So we get, ultimately we get our two normal parameterizations differ in the CK plus 2 norm by a constant multiple of epsilon. Call that star star. So the C0 part's easy to see. So the way you can see this is you write f after g of arc C. Remember, this is just your exponential map, essentially. So you can write that as the integral over the derivative of the exponential map. But the derivative of the exponential map is just the point. Sorry, it's just the velocity of the geodesic, right? So it's just C, right? Which is just Ci integral from 0 to r of EI. And then you can see that this estimate here will give you an estimate for at least the C0 norm here. The CK norms I'm a little bit unsure about, but the bounds on W should integrate up to bounds on the parameterizations. Okay. So in the last few minutes, we still need to show that M closes up as a cylinder, right? So far I've got these two parameterizations. It's very close to a cylinder, but there's no reason you can extend that all the way around and for it to connect together. We'll still need to show that. Okay, so you consider for this the y1 coordinate corresponding to the vector e1 of p. Okay, where the e1 of p is just from before. So it's the one pointing along both the cylinder and M. And we're just considering that coordinate, okay? And we want to consider the level sets of it. And we can assume, for instance, that y1 of p equals 0. Okay? Now, star gives us the following. So star, remember, was a comparison between the two frames. Okay? Star will give a comparison between E1 at arc C and E1 bar at arc C, right? However, E1 bar at arc C, well, E1 bar doesn't change because it's just the axial direction on the cylinder. So you just get E1 at P. okay, and this is less than C epsilon. Okay, and so for epsilon small enough, that means that the gradient of y1, which is just E1 of P, this is never going to be 0 in the ball. Okay, and that means that this level set, when I intersect it with BL of P, is a smooth hypersurface. Okay, so again, I'll just go here. So we have this cylinder. And what I'm saying is when you go along to, this is y1 equals z, when you go along here and you intersect with this plane, this is going to be smooth because we're staying fairly close to the cylinder. Nothing's degenerating. Okay. Okay, so we're nearly there. Because these two parameterizations are so close, okay, I can build an orthonormal frame on sigma z, so I'll call this sigma z. I can build an orthonormal frame on sigma z that's very close to the corresponding frame on the cylinder, okay? And because I can do that, because that's already close to the frame on my, the other orthonormal frame on M, then I can say the following. So I'll say star plus star star will give us an orthonormal frame. This is for I equal 2 to N. This is for, or I should say an adapted orthonormal basis, right? For this plane, such that, and then we want the sum from I equals 2 to N, and this compares nicely with the other frame we have. So we want to build a frame on here because we want to compare the Weingarten map to the identity. So it's convenient to build a frame to do that. But in any case, it's going to be close to the nice frame we have. So now, this is where we use our assumption L greater than or equal to 10, and we want to take Z between, well, we want to take Z less than L minus 1. I claim that there actually does exist a ball inside my hypersurface with radius bigger than 4, and this intersection is also C epsilon K spherical. So why is this true? Well, this just comes from like the geometry of the situation, right? So I've got a ball of radius L. Okay, and then if L is bigger than 10 and I don't go past L minus 1 in height, then it turns out this will be bigger than or equal to 4. Okay, so I do indeed have a ball sitting in there. Of course, you know, everything's very, you know, we're saying the geometry is close to the cylinder, etc. 4 should be more, 10 should be more than enough to fit a ball in. And then why is this C epsilon K spherical? Well, it's just essentially a computation, right? So you show that W, if I take the W at the point C and I subtract identity C, and I want to act on EI tilde, this is for I greater than or equal to 2, and then ultimately you want to use the fact that that this frame is close to the EIs without the tildes. Okay, so you know that EI minus EI tilde is small. And you also know that when you parallel transport back, right, that W minus ID acting on EI without the tilde is also small, okay? And so you're going to get that this ultimately is small as well. And so you get that a comparison between the identity in the Weingarten map of your hypersurface, and then you also need to show that the K derivatives are bounded as well. Okay, and then ultimately what this means is that by previous proposition 3.4, you're going to get that sigma Z is a closed, uniformly convex surface, and it's given by a graph. So a bit messy. Given by a graph U from S N to R, and this U will depend on Z.
I think it's n-1.
Yes. Yep, so it's given by a graph over Sn-1, and this U has CK plus 2 norm controlled. Okay, and then again, you use the assumptions on W, right? So the fact that the CK norm of W is so nice. This lets you extend U to a map over the cylinder. Okay, so sorry. And that roughly gets you home, right? So the idea is you do on each level set, you construct the spherical parameterization, and because the second derivatives of any graphical representation are so small, you should be able to glue these up and get a full cylindrical parameterization. Okay, oh, so that's right on the hour, so we'll leave it there. Thanks very much. Yeah, let me know if you've got any questions.
Thanks, James.
Thank you.
Yeah, I think you did a pretty good job there, getting through all that. Yeah, certainly not the easiest stuff to get through. Yeah, yeah. So very good, very nice. Thank you. Anyone have any questions or further questions beyond what we've already had?
Can this construction be extended to Sn minus 2 times out to something like that by some kind of induction or something?
I don't know, maybe.
All right.
Then do you know?
I think that should be possible. Yeah. If you had,
All right.
small control on gradient, second fundamental form, very small, and it's at some point it's close to the embedding of the standard S2 cross Rn minus 2. Then I think the same sort of argument should allow you to extend that.
Yeah.
Okay.
You slice with a two-dimensional
plane.
plane, you still get a small sphere in a lower dimensional space, and then so that's the first part of the argument.
Some kind of dimension induction or something. Right?
Yeah.
Okay, thanks.
Yeah, so the reason I was worried is because this oh, sorry. Go on.
No, I mean, you have to keep in mind that the result would fail if the dimension is small. So, for example, a two-dimensional surface in R3, even if you knew the second fundamental form was close to a standard cylinder, your argument that it closes up would fail. I mean, in fact, you could have a multiply wrapped cylinder, for example, to satisfy your conditions. But yeah, so really, you have to have the cross-section of dimension at least 2 to get it to work.
Yeah, true. But yeah, the reason I was worried about completeness is because a priori this intersection isn't complete.
Yeah, that's right. Yeah, I think you're right. You do have to worry about that. But the extrinsic geometry helps here. I think that things are close to an intrinsically something embedded into the ambient space.
Yeah, right. Okay.
So yeah, but yeah, I think you're right. It's not quite. You can't just apply 1A Myers out of the box.
But in that part of the proof, if the Ricci curvature is at least 1, for example, and then at the point P, the geodesic can go at least a distance of 4, then it should be complete.
Then you know there is a minimizing geodesic. That's right.
Yes.
Yeah.
All right. Anything else? Any more questions?
Great talk, James. What's
Thank you.
next?
Oh, next is so now we've got this cylindrical parameter. Well, next is my oral presentation for a PhD, and then the next week after that is
when is that
we're
happening?
doing
I should know.
next Friday.
Nobody tells me that. Next Friday.
Yeah.
Okay.
But then after that, probably the next Friday, we're going to look at sort of canonically parameterizing these things. You know, so you get some scale invariant parameters of the cylinder and things like that. So that you get enough conditions to get like a unique maximally extended neck. And then we're going to define a surgery algorithm on that neck that preserves the true convexity and things like that. And so then we should be in a position to get rolling with surgeries.
Right.
Very good. Yeah. Okay. We look forward to that. And I think next time Tim will be back to shepherd you through all the trials and tribulations of cylindrical estimates. Otherwise, we'll see you then.
Cool.
Yeah.